So good morning everyone. The agenda for today's session is we are going to first recall whatever we did last week since we are meeting after a week. So we'll just briefly recall whatever we have done. Then we will see what are KKT conditions, and then we will see an example, one or two example, and then one of the numerical method called as a steepest descent method. Okay, there's a numerical method to find the approximate solution. Now, till now we have seen what do you mean by an optimization problem, and we have seen that it can be categorized into two parts. So like one of the categorization was it can be categorized as a linear programming problem and a non-linear programming problem. And in non-linear also we have seen one particular type which was nothing but a quadratic programming problem. So linear means everything is linear. Your objective function, the constraints, everything is linear. In non-linear programming, either the objective function or one of the constraint or both are non-linear, then it's a NLP. In that case, we have seen a particular type of problem, which is a quadratic programming problem, because this comes a lot in practical world. So when a problem is said to be a QPP, quadratic programming problem, if your f, the objective function, can be written in the form of C transpose x plus half x transpose qx, subject to the constraints gi of x. So where your gi's are linear, so this is I'm talking about minima. We have always restricted our case to minima. The same theory goes for maxima as well. So when you have such thing, then if such a problem is called as a QPP, quadratic programming problem, your GIs are linear and your F has a degree 2. Okay, and this was one categorization, and then there we have seen the concept of CPP, convex programming problem. So when you call a programming problem to be a convex programming problem, if your objective function and the constraints all are convex functions. Okay, so when all of them are convex functions, then we call such a problem to be a convex programming problem. Okay, so this is what we have seen, and then we also observed that your LPP, linear programming problem, always sits inside the set of convex programming problem, because LPP means the objective function and the constraints are linear. Linear functions are always convex, so LPP is always a CPP. Then we have also seen that under some conditions your QPP is CPP. So if you recall, in QPP my GIs are linear, so I have to only worry about F. And then we have seen a theorem that when my Q is a symmetric, if you can recall, when Q is a symmetric positive semi-definite matrix, then your QPP is a CPP. And we also seen that why we multiply by 1 by 2 over here. The reason for multiplying by 1 by 2 because your Q actually becomes the Hessian of F. So this is what we have seen. So we are, and then I told you that we are happy when the problem is a convex programming problem. Why we are happy when we are having a convex programming problem? There's the answer to that is the KKT conditions. KKT conditions help us to find the point. Which point? So now let's try to answer that question. Okay, so this is what we have seen till now. Okay, so the first two pages are we have already seen in the last lectures. Now, why CPP are good? And that's where this KKT conditions help us. KKT, I don't remember the full form. Some Kurun something, K something, and T Tuhan something. These are the three people's name. My suggestion is you just read the Wikipedia page, okay, for more information. Okay, now what is our aim? So suppose you have optimization problem, minimization of f of x subject to the constraints gi of x less equals 0. Let me call this as problem P. You want to solve the problem P. That means what? You want to find the point of minima. Okay, so what is your aim? To solve the problem means what? to find x bar. What is your x bar? It is the optimal point. You can recall the definition from the first lecture, optimal point. Your aim is to find the optimal point. That means the point where the constraints are also satisfied and the function is taking the minimum value. So question is how to find this optimal point. Okay, so that's where the KKT condition comes into picture. So there, let me call as necessary conditions first. Necessary conditions. Actually, when you have a convex programming problem, these conditions are necessary as well as sufficient. I will tell you what do you mean by necessary, sufficient, and all those things. But first, let me just state the theorem. Okay, so if your x bar, I'm just telling in a very short and a simple way, but you just visit this page, okay, for more detailed information. Okay, if I talk everything, that will take a lot of time. But let me explain you these necessary conditions in a very simple way. Okay, so if your x bar is a point of local minima, if x bar is a point of local minima, that means your function is having the local minimum value at the point x bar. Okay, so x bar is a point of local minima, and that means what? Local minima for the problem P. That means it will satisfy the constraints as well. Okay, and suppose your problem P is a nice problem. Nice problem, so that's why I'm telling you to read this page. Nice means it's all the condition, like the constraints are good, your function, objective function is nice. Okay, then there exist multipliers called as the KKT multipliers. Then there exist multipliers, sometimes also called as KKT multipliers, lambda i's. Okay, some people denote by lambda I, some people denote by lambda I bar. It's okay. I is from 1 to m, such that my suggestion is you please write down this necessary condition, because we are going to solve a couple of problems. That time you will need this. Okay, so what are the conditions? The conditions are four conditions. There are four conditions. It should satisfy grad of f at point x bar plus summation of lambda I gi of x bar equal to 0. I don't know whether you have seen the concept of optimization in while studying multivariable calculus. Usually when people study the concept of local maxima, local minima and saddle point, after that there is a concept of this Lagrange of optimization problem. But anyways, this is nothing but the same generalization of that. If you don't recall, that is also okay, but those who can recall, they can just relate this with that problem. So your x bar should satisfy this condition: grad f plus summation lambda I gi is equal to 0. It should satisfy the constraints. When you multiply your constraints by the KKT multipliers, the product should be 0 and the KKT multipliers should be non-negative. Okay, so whenever you have a optimal point x bar, that means it's a point of local minima, then there exist KKT multipliers lambda I such that all the four conditions are satisfied. Okay, so if you have a local minima point, then these conditions are satisfied. So these are the necessary conditions. These are not sufficient. That means what? Converse is not true. That means if you have a point x bar where these four conditions are satisfied, but then that point need not be the point of minima. Converse is not true. So these are not the sufficient condition for a point to be a minimum point. Okay, so necessary condition means what? These are the necessary conditions for an optimal point. That means if you have an optimal point, then these conditions has to get followed. So these are necessary. Okay, but the converse is not true. That means these are not sufficient conditions for an optimal point. These are not an optimal conditions for a point to be an optimal point. That means if you have a point that satisfies these four conditions, then that point need not be an optimal point. That means that point need not be a point of local minima. Okay, I will tell you under what condition the converse is true, but for before that, let me take you an example. Let me give you an example. Okay, So let me take an example. So you have a problem P. What is the problem? I have to minimize minus of x. This is a very standard problem I have taken. Subject to, you have a circle x1 square plus x2 square less equal 4, and you have a parabola minus x1 square plus x2 is less equal 0. Okay, and my x1 and x2 are non-negative. So this is, I'm giving you the counter example. Okay, so what I have said, if you have a point that satisfies these four conditions, if you have a point that satisfies these four conditions, then that point need not be a optimal point. So here for this problem, we will see that 0, 0 will satisfy all the four conditions, but it is not the optimal point. Okay, why it is not an optimal point? You can see what is the region. Now x1 square plus x2 square less equal 4. What is that? It's nothing but a circle of radius 2 less equal. So this is the region. And x1, and what is this? This implies your x2 is less equal x1 square. That means your y is less equal x square. If you want to use the language of x and y. So what is this? This is y equal to x square. Y equal to x square graph. Y less equal x square means what? What do you think? The interior part or the exterior part of the parabola? What do you think?
Interior part, sir.
Interior. So this is the region. Okay. So let me remove this. X1 can be anything. Because if x1 is also positive, then only the first quadrant. So my x2 is also greater or equal to 0. So this is the required region. Okay. So this is the required region. And so can you give me the point in this region where the minimum value is attained? Can you give me x1 comma x2 where the minimum point is attained? This I have to, what is my function? My function is f of x1 x2 is minus x2. Can you tell me which point in this region your function will take the minimum value?
0, sir.
What is f of 0 0? F of 0 0 will be 0. Can you give me any other point where the value will be less than 0? It should be in this region. Other than 0 0, so at 0 0 the value is 0. But that is obviously not the minimum value. Okay. Does there exist a point where the value is less than 0? If I take 0 comma 2, what is f of 0 comma 2? 0 comma 2 means this point over here. What is f of 0 comma 2?
-2.
Minus 2. And obviously minus 2 is less than 0. Okay. So obviously you can see that the optimal point is 0 comma 2, because at 0 comma 2 the value is minimum. Okay. So at 0 comma 2 the value is minimum. So this is the actual answer for this problem. But what we are going to see that your point 0 0 satisfies this condition. So see what this I told you as a separate thing, that what is the minimum value. So answer is at 0 comma 2 minus 2 is the minimum value. But what was the main aim for this example? The main aim was I want to show the converse is not true. That means if you have a point that satisfies these four conditions, then that point need not be a point of minima. So here we are going to show that 0 0 satisfies this condition, but 0 0 is not the point of minima. And we can obviously see that 0 comma 2 is the point of minima. 0 comma 2 is the optimal point. Your 0 0 is not an optimal point. Okay. Therefore, this example works as a converse to the both theorem. Okay. So let's try to show that 0 0 satisfies all the four KKT conditions. Okay, and 0 0 is not an optimal point because 0 2 is an optimal point, because the minimum value is minus 2. 0 is not the minimum value. Okay, so let us try to write down the KKT conditions. Let us try to see whether 0 0 satisfies the KKT conditions or not. Okay, so what is the first condition? Grad of f at x bar plus summation of lambda I gi of x bar should be 0. And here I will go from 1 to 3. What is your f of x bar? It is nothing but minus x2. What is your g1 of x bar? Your g1 is nothing but the first x1 square plus x2 square minus 4. x1 square plus x2 square minus 4. What is g2 of x bar? What is g2 of x bar? Minus x1 square plus x2. Minus x1 square plus x2. What is g3 of x bar? My x2 is greater equal 0, means minus x2 is less equal 0, so it is minus of x2. So g1, g2, g3 and f. Okay, so these are my 4 constraints, sorry, 3 constraints and the objective function. Now what is grad of f bar? What is the gradient? Gradient is an operator such that if you apply the scalar valued function, the gradient is nothing but a vector consisting of partial derivatives. Your gradient is nothing but it's a vector consisting of partial derivatives. So this is f with respect to x1 and f with respect to x2, right? Those are comfortable with this, they can start solving this thing. Okay, so g1 with respect to x1, g1 with respect to x2 plus lambda 2 into g2 with respect to x2, sorry x1, g2 with respect to x2 plus lambda 3 into g3 with respect to x1, g3 with respect to x2, this is equal to 0. What is this? My function is minus x2, so with respect to x1 it is 0 and this is minus 1 plus lambda 1. What is g1? This is 2x1, that is 2x2 plus lambda 2 into or actually I don't even need g3 as well for this. Actually, even if I don't give actually my g3 is a redundant constraint. Even if I don't take x2 greater equal 0, still I will get the same region. Correct? Because what is the region? First one will give me x1 square plus x2 square less equal 4. So that is inside the disk. And this will give me inside the parabola. So obviously the common region is what? This is what the common region is. Okay. So automatically my x2 less equal 0 is a redundant constraint. Okay. So it's okay if you don't write it. Okay. So that's why I have just removed the third condition. X2 is greater equal 0. Automatically it comes out to be that. Okay. So why to increase the constraint and increase our load? Okay. So I don't need the third one. So I have only 2 constraints. Okay. So this is equal to 0 bar. Okay. What is G1 with G2 with respect to x1? It is minus 2x1 comma 1 equal to 0 bar. Now just multiply this inside. Let me go to the next page. What do you get? I hope you people are writing this along with me, or you can just listen to this. That's okay. Make sure the step by step things are clear. So this is 0. This is 2 lambda 1 x1 minus 2 lambda 2 x1. Okay. So 2 lambda 1 x1 minus 2 lambda 2 x1 equal to 0. Your second component will give you 2 lambda 1 x2. Okay, minus 1 plus 2 lambda 1 x2 plus lambda 2 minus 1 plus 2 lambda 1 x2 lambda 1 x2 plus lambda 2 equal to 0. So let me call this as equation 1. Let me call this as equation 2. So I get 2 equations from the first KKT conditions. I know that x bar this gi is less equal 0. Okay. What is the third one? My lambda I gi equal to 0. So lambda 1 into g1 of x equal to 0 means what? Your lambda 1 into x1 square plus x2 square minus 4 equal to 0. This is my third equation. And lambda 2 g2 equal to 0 means what? Your lambda 2 into what is g2? It is minus x1 square plus x2. This is equal to 0. Okay, so these are my KKT conditions. I want to show that 0, 0 satisfies all the conditions. I want to show that 0, 0 satisfies all the 4 equations. Okay, now if x1 and x2 are 0, 0, then what does your 3 implies? 3 implies what? Your lambda 1 is 0, because x1 is 0, x2 is 0. So I have minus 4 lambda 1 is 0, but minus 4 is non-zero, therefore lambda 1 has to be 0. Okay, and 2 implies my x2 is 0, so this implies my lambda 2 is 1. Okay, so if I take x1 equal to 0, x2 equal to 0, lambda 1 equal to 0, and lambda 2 equal to 1, then all the KKT conditions are satisfied, right? They are satisfied. You can check. What is the fourth condition? My lambda i's has to be non-negative. Are they non-negative? Yes. My lambda 1 is 0 and lambda 2 is 1. So they are non-negative. Good. Is my third condition satisfied? Yes. That means is equation 3 and 4 satisfied? Yes. You put 0, 0. So fourth condition is satisfied. Here you put x1 0, x2 is 0, and your lambda 1 is also 0. So the product is also 0. So equation 3 is satisfied. So therefore this is satisfied. Are the constraints satisfied? Yes, because you can see that here your 0, 0 is in both the constraint. This 0, 0 point over here is in both the constraint. That means it is satisfied. Or you can check, you can put the value 0, 0. It is satisfying both the condition. Is it satisfying the first condition? Yes. That means is it satisfying the first two conditions? Yes. You put x1, x2, 0, 0. So 0, 0 will give me 0. My lambda 1 is 0. My lambda 2 is 1. So 1 and minus 1 is 0. So all the conditions are satisfied for this x1, x2, lambda 1, lambda 2. But is this an optimal point? Answer is no. Okay. So we have seen that for this example, my 0, 0 satisfies the constraints. That means 0, 0 satisfies all the 4 conditions, all the 4 KKT conditions, but it is not the point of minima.
Sir,
Bolo, yes.
sir, if this test is not giving us the minimum optimization point, then why we are using this test?
So if you have a point that is an optimal point, then these conditions are indeed satisfied, but the converse is not true. When is the converse true? When is the converse true? So answer is, if your problem is a convex programming problem, that means what? If your f and gi's are convex functions, if your f and gi's are convex functions, then the converse is also true. That means what? If you if you have a point x bar, which is a feasible point, okay, not an optimal point, I'm saying, that means it is a point in the constraint. If your x bar satisfies KKT conditions, if your x bar satisfies KKT conditions, then x bar is a point of, then x bar is an optimal point. Then x bar is the optimal point. So that's why from starting I have been concentrating on CPP. Why I was telling that CPP is important, this is the reason. So see, whenever you have a problem, your job is to find that optimal point. And KKT proved that when you have a convex optimization problem, then these conditions are necessary and sufficient. So you try to find the point which satisfies the 4 conditions. Once you have a point and the KKT multipliers that satisfies this condition, then automatically that becomes the optimal point. Okay, so converse is not true in general, but when you have a convex programming problem, then the converse is always true. Okay, so you can apply this KKT multipliers to LPP problems whenever you have a linear programming problem, or in quadratic programming problem, if your Q is symmetric, positive, semi-definite. We have seen that when Q is symmetric, positive, semi-definite, then your QPP is a CPP. So when you have such problems, then you can always use KKT conditions to find an optimal point. Okay, so KKT conditions ka converse is not true in general, and we have given the counter example. So when it is true, when it is a CPP. Okay, so let us take an example so that it will be more clear. Find, okay, not find will take some time. So let me directly tell you. Show that, or write down the example. Minimize the problem P. Problem P is what? Minimize f of x bar as x1 minus 9 by 4 square plus x2 minus 2 the whole square. Okay, so here you can, is this a convex programming problem? Is this a convex programming problem? When I will say something is convex, if f and gi's are convex functions. Is my f a convex function? Yes, because it's linear, right? So it's linear, therefore it's a convex function. Is my g1 a convex function? Do you know, can you recall what will help you to check whether a function is convex or not? If I take g1 to be x1 square plus x2 square minus 4. Is this a convex problem? Find the Hessian of G1. What is the Hessian? Can anyone tell me what is the Hessian? I am solving side by side, but if someone can tell me before I get the answer, it will be good. Okay, so I got the answer. So this is the Hessian, and you can see that this is positive definite. How do you check whether something is positive semi-definite or not? You just see the principal minus. That means delta 1. It is nothing but the first entry, which is positive. Delta 2, which is a determinant of this matrix, which is also positive. Therefore, yes, this is a convex function. What is your G2 of x bar? Minus x1 square plus x2. Is this a convex optimization problem? Is this a convex function? Can anyone tell me what is the Hessian? What is the Hessian for this?
minus 2
0
1 0 1.
1, no? Okay, fine. So you can see that a delta 1 is not greater than 0. So your G2 is not a convex. Okay, so in this problem which we took earlier, this was not a CPP. Okay, if it would have been CPP, then the converse is also true. So you can see that this was not a CPP, the earlier problem which we took. Okay, so now let us take a CPP so that the converse will also be true. So for that, instead of finding the point, I am giving you the point directly. Okay, so first write down the function. I have to minimize x1 minus 9 by 4 whole square plus x2 minus 2 the whole square subject to x1 square less equal x2, x1 plus x2 less equal 6, x1 greater equal 0, x2 greater equal 0. Okay, actually I was going to tell you fine, but let me just tell you show that 3 by 2 9 by 4 is a optimal point, or is an optimal point. Okay, so whenever you want to show something or you want to find, first thing is check whether the given problem is a CPP or not. Okay, so step 1 is the given NLP. It's a non-linear programming problem because degree is not 1. Is the given NLP a CPP? That's what the first question is. So let's try to find the Hessian for each of the matrix. What is the function f of x bar? X bar means x1, x2. Can anyone tell me what is the Hessian coming out to be? Anyone tell me what is Hessian is coming out to be? F with respect to x1 is 2 x1 minus 9 by 4. F with respect to x2.
The 2 0
Okay, 2 0 0
and
2.
Yes, sir.
Okay, good. So is this convex? Yes, actually you can say this is strictly convex. Okay, because my delta 1 is strictly greater than 0, my delta 2, the determinant, is also strictly greater than 0. Okay, so your f is a strictly convex function. Okay, when equality comes, you can simply say convex. Even if you say convex, no problem. But I will tell you a reason why I'm telling you strictly convex. Okay, that's one thing. Okay, what about G1? G1 is nothing but what was the constant I wrote? X1 square minus x2. Is this a convex function? Can you find the Hessian? G with respect to x1 is 2x1 and G with
Sir,
respect
2, 0, 0 minus 1.
2 0
0
0
minus 1.
minus 1.
Yes, sir.
Then it won't be convex. Can you check again? So G with respect to x1 is 2x1. G with respect to x2 is minus 1. You have to take the second order derivative. G x1 x1 will be 2. What will be G x2 x2?
0.
Okay, so that happens in a hurry, no? We just differentiate once and minus 1 derivative is 0, na? So you can see that delta 1 is positive and delta 2 is greater equal 0. So yes, this is positive semi-definite. Therefore, your G2 is also convex. Your G2 is always also a convex function. Similarly, homework, try for G2, G2, G3 and G4. Okay. So what is your G2? Your G2 is nothing but x1 plus x2 minus 6. Actually, it's a linear function. So directly you can say it's a convex function. G3 is what? Minus x1. This is also linear. So this is a convex function. And your G4 is minus x2 because x1, x2 are greater equal 0. We always write less equal. That's why I'm writing minus x1 and minus x2. This is also linear. So this is also a convex function. So therefore this NLP, this is not a QPP, okay? Because the first constraint is not linear. So this is not a QPP. This is an NLP, and this NLP is a CPP because all F and Gs are convex. Good. So this is a CPP. So I can take help of KKT conditions. Now let us see whether the given point satisfies the KKT conditions or not. That is my step 2. So what is the point given to us? 3 by 2 and 9 by 4. So using this point, if I get the KKT multipliers greater equal 0, and if this point and the language KKT multipliers are satisfying, then great, then this will be the optimal point. So let us try to see. So what will be the KKT conditions now? Grad f plus lambda 1 grad g1 plus lambda 2 grad g2 at x bar. I'm not writing x bar. At grad g3 plus lambda 4 grad g4 equal to 0. What is grad f? It is twice x1 minus 9 by 4 comma twice. This is actually very big, so I'm just going to solve half of it and I will give you rest as a homework, so otherwise this will take a lot of time. What is grad g1? It is 2x1 and minus 1 plus lambda 2 into grad g2 1 comma 1. Don't write, you can just see whether if this is clear or not. If this is clear, just give me thumbs up if this page is clear. Plus lambda 4 into 0 comma minus 1. Is this clear whatever I have written in step 2? Okay, good. I can see some thumbs up. Okay, good. Okay, I have simply taken the gradient. That's all. Now, what does the first component implies? So twice x1 minus 9 by 4 plus twice lambda 1 x1 plus lambda 2 minus lambda 3 equal to 0. And second condition implies, or let me write on the next page. That will be good actually. So what is the first condition? 2 times x1 minus 9 by 4 plus 2 lambda 1 x1. If someone is very much comfortable, then he or she can solve along with me. or you can simply listen and make sure each step is clear. You can solve this later on. And what does the second component implies? 2 times x2 minus 2 minus lambda 1 plus lambda 2. From second line I have minus lambda 4. Okay, good. So this is my first condition and second condition. This is I'm getting from the first condition of KKT. GIs are less equal 0, that I have lambda I GI is equal to 0. That means lambda 1 into what is G1? G1 is x1 square minus x2. Lambda 2 into G2. G2 is x1 plus x2 minus 6. Lambda 3 into minus x1 equal to 0. And lambda 4 into minus x2 equal to 0. Now I have given you the point. What is the point? 3 by 2, 9 by 4. So my x1 is 3 by 2, x2 is 9 by 4. So let me give you 3, 4. Just listen what I'm doing. I will do a bit fast. So just listen. So this is the point given to me. From this, what can you say about lambda 3 and lambda 4? Use equation 5 and 6. What can you tell me about lambda 3 and lambda 4? 0, 0. Good. Lambda 3 is 0, lambda 4 is 0. Right? Because my x1 and x2 are non-zero and the product is 0. Therefore, lambda 3, lambda 4 is 0. Okay, good. Again, now when I put 3 by 2 and 9 by 4 in equation 4, what my 4 will imply? Will it give me anything about lambda 2? If I put it in equation 4, what I have? Lambda 2 into 3 by 2 plus 9 by 4 minus 6 equal to 0. So lambda 2 into, what is this? 3 to the 6 plus 9 by 4 minus 6 equal to 0. Lambda 2 into, what is this? 9 plus 6 is 15. 15 by 4 minus 6. So obviously 15 by 4 minus 6 is a non-zero number, and therefore this implies your lambda 2 is also 0. Okay, so equation 4, 5, 6 will tell me that 3 by 2 and 9 by 4 will force lambda 2, lambda 3, lambda 4 to be 0. If I put this point x1, x2 in equation 3, will it give me anything? Answer is no, because x1 here 3 by 2 square is 9 by 4 and minus 9 by 4. So this is 0. So you can't tell whether lambda 1 is positive or not. See, what I want, my lambda 1 should be greater, all lambda i's should be greater or equal to 0. So now equation 3 is not helping me. So let us take the help of equation 1 or 2. So if I put this in equation 2, suppose, then what will I get? My lambda 2 is 0, my lambda 4 is 0. I can get the value of lambda 1. Can someone use equation 2 and tell me what is the value of lambda 1? My lambda 2 is 0, lambda 4 is 0, our x2 is 9 by 4. Use x2 equal to 9 by 4, and can someone tell me what is lambda 2, lambda 1? I am getting 1 by 2. Did anybody get 1 by 2?
Sir.
Okay, good. So you can see that, you can ignore, write it later on. You can see that if I take x1 equal to 3 by 2, x2 is equal to 9 by 4, my lambda 1 comes out to be 1 by 2, my lambda 2, lambda 3, lambda 4 comes out to be 0. So these are the points I'm getting. So I'm having x bar and I'm having KKT multipliers greater equal 0, such that all the conditions are satisfied. And now since this is a CPP, step 3, since the problem P is a convex programming problem, therefore by KKT condition, by KKT theorem, the converse is also true, we know that. By KKT theorem, 3 by 2, 9 by 4 is an optimal point. Is an optimal. Okay, so that's how one can use KKT conditions to find. Actually, finding would have been quite difficult. That's why I directly gave you the point. So this is an optimal point. Actually, there is actually a very nice theorem. Actually, this point is a global minimum point, matlab absolute maximum. Global. This is not a local minima. This is actually this is a local minima, but there is a nice theorem. From that we can conclude this is a global minimum point. I don't know whether you have seen this in convex functions or not. I will just state it for your reference. So there is a nice theorem that says that if you have a function from S to R, where your S is a subset of Rn, okay, your S is a convex set, your S is a convex set, and your F is a strictly convex function. If your F is a strictly convex function, then there exists a unique, actually not global, I want to say this is a unique minimum point. That means there is no other minimum point. Okay, this is the only one. The theorem is there exists a unique minimum point of F over S. Can anyone, have you seen this theorem? Can you recall? Yes, no, anything? While studying convex sets. Okay, even if you have not seen, you can take this theorem into consideration. Now in our problem, what was the function? Our function was x1 minus 9 by 4 the whole square plus x2 minus 3 by x2 minus 2 the whole square. Now here what is your S? It's a complete R2 because you take any x1, x2, you have an output. Okay, so F is defined for every point in R2. So your S is R2 and the complete set is obviously a convex set. Is your F a strictly convex function? Is your F a strictly convex function? Let us see. You have found the gradient. Yes, we have seen over here that your F is a strictly convex function. So yes, so your S is a convex set, your F is a strictly convex function, therefore there exists a unique minimum point. We have already shown that this is a minimum point. So therefore this has to be unique because it cannot have more than one minimum point. Okay, so actually one can say that this optimal point is a unique optimal point thanks to this theorem. Okay, good. So that was the upshot of this, that why I was always stressing on CPP. Okay, so convex, whenever you have convex sets or convex functions, you can be relaxed, little bit relaxed because you have KKT conditions. Okay, so that's the first thing usually people do whenever they have a problem. They try to see whether it's a CPP or not. Okay, but what if it is not CPP? Okay, so when you have CPP, good, things are very easy. You have KKT's conditions. If not, then what to do? Okay, then there are some numerical methods that helps you to solve optimization problems. Among them, the few are steepest, the few that we are going to discuss: steepest descent method. Second is Newton's method. Everybody might have seen Newton's method while finding the roots. This is nothing but the generalization of that. And the third one is the penalty function method. Penalty function method. So today we will talk about steepest descent method, and tomorrow we will talk about the remaining two methods.